sono där och hållit. Mi maski man den kommer inte att jag
Excuse me, can you hold this?
Accordion tired.
No, just for the time that I introduce, and then after that I come and I sit there and I will hold it.
Okay.
But hold it steady though. Don't shake.
I'm doing so well. Like, how dare you judging?
It's a blackberry. Yeah.
I can hold it.
If you do it like that, the whole thing. Yeah, it's not a dimension, so.
No, yeah, that's alright. That's fine. I knew it was gonna come to this.
You're doing great.
I know.
It seems like you've done this before. Man, actually.
What is off for long?
Wil je een foto zien?
Das ist schon gut. Irgendwo ein Video von dir, das ich mir anschauen kann. Das finde ich aber schon noch cool.
Ja, ich bin so mal Schatz. Dat is niet zo. Alle kinderen. Ja, aan de ene kant wel, maar aan de andere kant. Het eerste wat ik met de ouders dan zei.
Nö, halt jetzt zu machen selber. Aber ich sollte so lange halten, bis er vorne was machen, danach wird es
Hello everybody! We're about to start this new Talk Cosmic to Me. I want to thank all of you for coming here tonight. Despite the heat, despite the rain, despite everything. It's really nice to have you. We're sorry you don't have AC in here, but we have a nice cool breeze for those people. You are getting toast. Tonight we are having a talk by Anna Escorza. She's a PhD student at the KU11 and at the ULB, and she will be talking about the double star systems, like Tatooine. Because some people ask me, why Tatooine? Because Tatooine has a double star system. Spoilers. Oh, yeah. She knows more than me. After that, we have Thomas Diot, who is a member of the collective Ice Screen. Ice Screen, this is good, yeah. He's an illustrator, he's got Instagram, and he will share it at the end. And he will draw live on space pictures using this nifty tablet, and you will see live the drawing, so it's pretty nice. Talk Cosmic to Me, for those of you who don't know what it is, it's a space talk. We're having this every 2 months in a different bar in Brussels. It's entirely free, all the time. It's done by just one person who is currently hiding in the corner right there. Because she loves the attention. And it's voluntary work, so please give a lovely round of applause. Yeah, she loves that part. We have a little bit of, if you want to show your love a little bit more, you can inscribe your email address in here if you want to stay up to date to what is going on, or even say a nice word. She will read it, you know, and then blush in silence. And then after that, we have all those social media that went way too fast, that you can subscribe to, and the next one, the next Talk Cosmic to Me, will be held in August, and it's a special one because we will be outdoor for the second time. I think it's the second time, yeah. Third time! Jesus Christ, the time goes by. And we will be at the Guinguette de Forêt, so in the park. So it will be nice because the stars, because a lot of things. So stay tuned, we don't know yet exactly the date, we don't know yet exactly what's going on, but we know where it is. Stay tuned, stay on those social media. They're playing with me. And without further ado, I'm leaving you with Anna Escorza.
works, but it doesn't move. 1 second. Yeah, now it moves. Okay, so now I can start. Hello everyone, and thanks for coming. Do you hear me properly? Let's test this thing first. Yes? If not, I can speak louder. So, no? Okay, so first, thanks to Celine for inviting me. And I want to start with an apology to those who thought that they were coming here to a dancing show, because that's not going to happen. And you cannot leave anymore, I'm sorry. You are stuck, yeah, through the window. You are stuck in a science talk now. I am here to talk about stars. I will start talking about the stars in general, how they are formed, how they live, and what happens during their life. And about halfway through my talk, you will be experts in stellar evolution. And then we will put a partner. We will see what happens when one of these stars gets a partner, and when they dance, and yeah, these things. I'll tell you later. So first, why do we care about stars? Why FAO is giving me money from your taxes to look at the stars 8 hours per day or more? Stars are the factories of everything. The oxygen that you are breathing, the beer that you are drinking, all the chemical elements that we know apart from hydrogen, helium, lithium, beryllium, and boron, and these ones here that I'm not going to name, and were man-made. All the other chemical elements were made in stars. Some of them are made in large stars, we will see them later, some of them in the smaller stars like the sun. And the thing that they have in common is that when these stars die, all these elements go out to enrich the universe, and they make it here for you to drink them or breathe them. So it's pretty important. If we don't understand the stars, we don't understand anything. So let's look at the stars. This is a big group of stars, or globular clusters for the expert. And these stars are very close together, born more or less at the same time, and all of them at the same distance. Do you see different type of stars here in this image already? We start doing science already from the first slide.
Red and white ones.
Yes, and blue ones. You left the color out. Red and blue and white, brighter.
Small and big.
Yes, small and big, brighter and fainter. So we just did science. That's how it is. That's why I'm paid for. In a few minutes, I will tell you how stars evolved, and we will come back to this image, and then you will be able to tell me as well which ones are bigger, which ones are smaller, older, younger, more massive, which ones are about to explode as well. So let's start. How do stars form? The stars are formed in clouds of gas, like this one over here, which is a star-forming nebula, big cloud of gas lying around in the universe. These clouds are there, somehow in equilibrium, and at one point something happens that breaks this equilibrium. Okay, so this cloud, it has a lot of material, so it will start breaking in pieces, and each one of those pieces that the cloud breaks into will form a star. So you will form stars like the sun, or the stars bigger or smaller than it, depending on where in the cloud we are, and depending on what broke that equilibrium. Since astronomy is all about pretty picture, let's start with a pretty picture of a star-forming region. So this is the Orion Nebula. If you have a telescope, you can point at the sword in the Orion constellation. Do you know the Orion constellation? Yes? It appears later in a picture. So this guy has a belt and a sword. If you point your telescope, that you don't need a super big telescope to be this. It's a huge patch of the sky, and it's forming stars. And we don't see the stars behind, because the cloud of dust is still there. So the starlight, the dust is obscuring the starlight for us. If we look at this same picture in the infrared, for example, so a completely different type of light that our eyes cannot directly see, then we will see the stars. But dust is opaque to human eyes. So this is a famous and visible in the sky, not in Brussels, not today. But if you have a telescope, you can look that way. And now we are going to form stars. As I told you, we will form stars like the sun, bigger and smaller. And the amount of material that forms each star is going to define everything in the stellar life. So everything that happens from now on depends on how much part of that cloud formed that star. So since in astronomy we work with very big quantities, I'm going to define one unit that I will be using probably more often than I should, which is the mass of the sun. So we measure the mass of the stars. The mass is the weight, the amount of material, how heavy a star is, and we compare them with the sun, all of them. Because if not, we will be talking about a lot of kilograms. So the mass of the sun is 2 and 30 zeros after the 2 kilograms. So you can imagine that we don't want to spend our day saying this number, so we just call it solar mass. So from now on, when I talk about a star like the sun, I will say that it's a star of about 1 solar mass. And when I talk about a star bigger, like that one over there, I will tell you that it has 10, 15, 20, 100 solar masses. Okay? From now on, if I mention a concept or a word that I haven't explained before, interrupt me and I will do it. Because if not, we are not going to understand and continue together. So this is one that I know I mentioned a lot and I wanted to explain to you, but it might happen again, so stop me and say, explain that. Solar masses. We go from here. So we have a star like the sun. How many solar masses does this star have?
Wow.
Yes, okay, we are still together. So a star like the sun will spend most of the time of its life burning hydrogen into helium in its core. Very quiet, doing nothing more. Thanks to that, we are here today. If the star was less of a boring star, we wouldn't be here. And it will be doing this for longer than we will be doing this, so no worries. And it will evolve. When the fuel is finished in the core of the star, it will expand, it will cool, and it will get very big. There is I am hearing myself. Okay. When the sun gets to the red giant phase, it will reach a size that the atmosphere of the sun will reach where the Earth is now. So that's how big, for comparison, how big the sun is going to become when the fuel finishes burning in the core. After this stage, there is a very short phase, but very pretty, in which the star that has very strong winds will throw all the material with the new chemical elements that it produced will be thrown to the universe. So there is this very short phase in which the core of the star is still there and it's able to illuminate that material, and that's how we get the pretty pictures of the planetary nebula. So this is a just dead star. Sounds very sad if I say it like this. So it's a just dead star, which is the core of the star is somewhere in the center, and all this is the dead body of the star, all the material that formed part of the star before, that was thrown through stellar winds, and that are illuminated by the core still. So this material will slowly expand and disperse, and the core will stay there. That's what we call a white dwarf. So white dwarfs are the dead core of a star that will not burn anymore. Is basically crystallized carbon and oxygen. So crystallized carbon, that's diamonds. So the sky is full of diamonds. Just a funny note. And the rest of the material will go and form a cloud somewhere else. So that will give birth to second generations of stars that will be more metal rich because of the materials that these stars have produced. So now we go to the other side of the diagram. More massive stars, they live much shorter. The more massive than the star is at the beginning, the shorter it will live. So it will be, everything will happen much, much faster. It will also have a red giant phase, but in this case it will be a red supergiant, so much bigger than before. And these stars don't have quiet deaths like the small stars. These stars explode. So it reaches a point in which the star is not burning anymore. So it cannot hold all the material that it has. The material falls on the core, and the core cannot handle it and explodes. So that's what we call the supernova, and it also produces pretty pictures. So this is a supernova remnant. Sometimes they are confused with the planetary nebula because it's funny shape, bright colors, but This is the dead body of a much more massive star than the previous one. Okay, so the product of this star when it dies will be a neutron star or a black hole, depending again on the initial mass of the star. I told you that everything depends on that. Okay, so now we know stellar evolution. We are all experts, so we can go back to this picture. And you know already, for example, that, I don't know, this blue star was initially more massive than this white star over here, because the stars like the sun don't become blue. You know that the red and big guys are about to die. Yes, yeah, so we can even zoom in, and it's the same cluster and from much closer. And we can, if the internet lets us, organize this star with the with the properties that we know. So we are going to zoom in this cluster, and we are going to organize them by color first. Okay, so now we are going to bring all the blue stars to this side and all the red stars there. And now we are going to organize them by brightness. The bright stars go to the top, and the faint stars go to the bottom. And just like this, we have created one of the diagrams that astronomers use every single day. And there are astronomers in the room. Tell them if I'm lying. We look at these things every day. So it's organized, as I told you, by color, which is proportional, related to the temperature of the star. Hotter and bluer to this side, and redder and faint in there. And just a curiosity note here, I don't know if you noticed, but the tap of your shower is lying to you. Bluer is hotter. And then in the y-axis of these diagrams, we have the magnitude, the brightness, luminosity of these stars. When the stars are burning hydrogen in the center, which is what we call the main sequence, the longest part and quiet and boring part of the life of the star, they lie on this part. And when they have finished burning the fuel in the interior is when they evolve this way and become the red giants or red supergiants that we saw before. So if we are able to locate the star on this diagram, we can know how massive it was when it was formed, what is happening on its life, and how it will die. So just a summary, we have the sun with 1 solar mass. We have a lot of the stars that are much smaller than the sun. The problem is that they are very difficult to study because they are not very bright, and for us it's more difficult to do the job there, but the closest star to the sun is a tiny one. And then we also have the huge guys over here, the blue stars that are more massive initially but still young, and then the red giants and red supergiants that are the about to die stars version of the other three. So I convinced you already that when you look up, stars are very different. Not all the stars are like the sun. So when you go out today or a day with better weather, you can look up and you can find a red star and a blue star, and you can distinguish some of them by eye, even in Brussels. And now I'm going to move to the second part. I told you that after I made you experts on stellar evolution, I was going to show you what happens when a star gets a partner. So how all this picture changes if the star, when it's born in the cloud, it's close enough to another star to start living together. So they are not close enough to become one, but close enough to start orbiting around each other and spending their life like this. So yeah, my sentence there was that not all sunsets are like in the sun, how are the sunsets in the sun? Not all sunsets are like in Earth. So this is advertisement for Belgian astronomy. This is a sunset from La Palma. La Palma is an island in the Canary Islands. And the K11, together with the ULB and the Royal Observatory, have a telescope there. So also your taxes go to this guy. And every night of the year, apart from a tiny break of 5 or 6 days that we take in Christmas, there is a Belgian astronomer or a Spanish astronomer working in Belgium, spends the night there and collects data for all of us to work. And this is how the sunset looks like there, on top of the sea of clouds. It's very pretty. And this is another famous sunset. Probably you have seen this one more often than you have seen the other. Yes? Tatooine, yes. Should I admit that I'm not a Star Wars fan and people will throw things at me? Yes, so this Tatooine is a planet that is orbiting around 2 stars instead of 1. We are used to the sun because that's what we see every day when we wake up. But a planet going around 2 stars or being in the system with 2 stars, it can be around 1 and the other one around the 2, but we are not going to enter that. A system with a sunset of 2 stars is probably more common than a sunset like the one we see in the morning. Only graph from a paper that I have, I promise, and I'm going to make it pub-friendly. In the x-axis, we have the same thing we had before in the diagram that I showed you. So here we call it the spectral type, but it's the color or the temperature that we showed before. These letters are random, because in astronomy we have a lot of things that are named randomly. I really don't know how this ended up like this. They found the star A, and then they found B that was brighter, and then, I don't know, F and G, and yeah. In several languages we have a sentence actually to remember this. I know the English one, I don't know the Spanish one, I don't know if someone knows, but to remember the order we learn O, B, and I, O, be a fine girl and kiss me, and then L and T, I don't know. But yeah, temperature, color. In the y-axis, we have what we call binary fraction, which means if I am looking at 100 stars like the sun, how many of them have a companion? So for stars like the sun, it's actually 50%. So if you look at 100 stars like the sun in the sky, 50%, so half of them have a companion. Might not be detectable, might be too close for you to see them separately, might be dead already, but that's what people think. And as you can see, the binary fraction goes up to 100% for the blue stars. So there are a lot of binaries out there. And I'm going to prove this to you, showing you that a lot of famous stars that you can maybe even point in the sky are actually in binaries. Which is the, I think I heard it over there already, which is the brightest star in the night sky? Sirius. I have to put the night here because I did this talk once without the night, and someone told me the sun. The brightest star. So no, we are talking about the night sky, and yeah, it's actually Sirius. And I have here Orion, just to go back to the nebula before, is somewhere over here. And if you look at this constellation, next time you see it, because this is one of the easy ones to find, check at the different colors between Betelgeuse and Draco.
Oh, she doesn't know.
What? Yeah, I don't know how to pronounce it. But this is a red supergiant, and this is a blue supergiant. And that one is actually a quadruple system as well, so talking about binaries and multiple systems. So Sirius, brightest star in the night sky, has a tiny companion. That's an artist's impression. We actually don't see it. I will tell you later how we know that it's there. But it has one of these diamonds that I showed you before, the white dwarfs, the dead body of a star like the sun. And they are orbiting around each other. And it makes you wonder if that guy is dead already. How was the system before? What happened when the star expanded and so on? We'll see later how these can reach this point. But yeah, so we have a binary system there and a quadruple system here in the same picture. The closest star to the sun. So I told you that the brightest is a binary, the closest is also a binary. So the closest star to the sun is Proxima Centauri, which is not a binary. When I talk about binaries, I mean multiples. So 2 or more. I should say but multiple systems instead of binary systems, but I'm used to the other word. But Proxima Centauri is slightly closer to the Sun than Alpha Centauri, and this is the triple system with it. So Alpha Centauri is actually 2 stars, and Proxima Centauri is in a triple system with the 2 of them. So the closest star to the Sun is also a multiple system. One more example of a famous star. Can someone find a constellation in this painting from Van Gogh? Yeah, that's it. So the second star in the... Oh, I had a pointer of this time. The second star, yeah, in this constellation is 2 stars that we are actually not sure if they are gravitationally bound to each other. We are not sure if they are in a binary system or not. If they are moving very slow together because we see them moving in the same direction. We don't see the binary motion. But I'm not lying to you because each one of these stars is a multiple system itself. So right now I am not sure which one. It's in a binary system, so 2 stars. Someone knows? No? Mizar is a binary system?
It has 2 spots there. So
yeah, but the other one is a quadruple system, so then it should have 4. But sorry, I could lie to you, but I'm not going to. I don't remember which one. One of them is a binary star, so 2 stars, and the other one is a quadruple. So if we end up proving that Alcor and Mizar themselves are moving together as well, we will be talking of a sextuple system with 6 stars. So that one, these 2 are supposed to be easy to differentiate, like to see the 2 of them by eye, but I never had very good eyes, so I'm not sure. You can try. But definitely you are not going to find the 6 of them. So now I told you that, that I could teach you, so this is when it gets a little bit technical, how we can know that a star is a binary system or a multiple system. I'm going to show you 2 techniques that we use very often. The first one is eclipsing binaries. So we have here a system, a binary system, also artist impression, no real picture. And we have a telescope with a camera just collecting light, pointing at them. So we are looking at these stars for very long, just collecting light, all of it. And again, if the internet lets us, when the stars, they are at the right inclination, that when they are orbiting, one passes in front of the other and covers the light. So obviously when we are seeing 2 stars, we are seeing much more light than when one of them covers the other. This technique, it's also the way we have found most of the exoplanets that are known. When a tiny planet crosses in front of a star that we are monitoring. So eclipsing binaries, technique 1. And then technique 2, spectroscopic binaries. This is a little bit more complicated, but we'll go through it. This is a spectrum, well, these are a spectra of different stars. It's the electromagnetic spectrum, it collects, so this time our instrument is not collecting all the light of the star at once. It's putting in different pockets the light that a star emits at different colors. Call it color, call it wavelength, call it frequency. So at each color we see that the star receives light and it collects the light. You have here again the "Oh, be a fine girl and kiss me" thingy. So bright stars on the top, cool faint stars at the bottom, and their names, which we don't care. And you see that they look different. These spectra show you black lines at different points, different colors, different frequencies. What this is telling you is the atmospheric composition of a star. So this line over here, whatever, is telling you that a specific atom is blocking the light because of the atomic properties that we are not going to enter in, is blocking the light and you don't receive it. That's why you have a black band. Okay, so this technique allows us to know what the surface of the star is made of. But when the star is in a binary system, and sorry I didn't find any newer one, this looks like from the 80s, These lines, the lines of that the atoms form, the absorption lines that we call them, are moving when the star moves away and towards you. So I think, I was trying to figure it out before, I think A is the red one if we look from here, so probably we are looking from a, let's put it again. Sorry. Nothing happened. So if we put our telescope on the top of this system, when the red star is moving towards the telescope, we'll go again, the B lines moves towards the blue, and when the red star moves away from the telescope, they move to the right. So this is the same effect that tells you when you hear an ambulance, it tells you if the ambulance is coming towards you or leaving. It's what it's called the Doppler effect, and what it produces is a shift of the frequency or the color or the wavelength of a wave, in this case light, in the case of the ambulance sound. So there is a shift in the frequency or the color in this case, depending depending on the source, the direction in which the source is moving. So if the source is moving towards you, you hear the light, the line moves towards the blue. Okay? Pay attention next time. What, sir? Are you asking me a question? Yes.
Can I
Yes,
make
yes.
a question already? So is it the point that then the stars will move in opposite orbits, and then the one line will be towards the blue and the other towards the red?
Yes, that's what you see in... Let's try not to make the microphone angry. So this is what you are seeing here. So you have here the light of both stars at the same time. Because normally when we point the telescope, they are too close for us to choose which one we want to look. So you will see light, you will see lines that they might belong to the same atom. And the line belonging to one star is moving towards the red and the other one is moving towards the blue. So what we need is to look at the same star several nights, and when you see your lines doing like this, in the spectra is when you know that there is a companion there. Sometimes you see only the light of one, if it's much brighter than the other one, and you still see that line doing like this. For example, Sirius, that will be the case, right? The companion of Sirius is not bright enough for us to see the light. But we see the absorption lines in Sirius doing like this if we observe it several nights in a row. No? This is... Oh, it's not going. Okay, let's do this. Yes.
Is it possible that from the point of view of the Earth, you don't actually get to see any eclipse, and therefore you miss?
Yes, yes, that happens in a lot of cases. And also you need to be looking at the right time to see the eclipse. We don't have infinite time to look at all the stars at the same time. But yeah, for example, that's when we use the spectroscopic binary technique. So if a star, if this, my hands are two stars, if they are with this inclination, you see the eclipse. But if they are, for example, like this, you don't see eclipses anymore, but you still see when they move towards you and away from you. So there is an inclination effect that makes us, so that's why the spectroscopic technique is much stronger, because the range of orbital inclinations in which you can use it is much wider, yes. Okay, so now we know stellar evolution, and we know that a lot of these stars evolve together with a companion. So you might be wondering already what happens if these two stars had different masses when this binary system and the stellar system was formed, and one of them reaches that stage of its life in which it expands. Like, do you think that guy will like it? Do you think it has a choice on what is going to happen here? So that's how we answer the question. Does it take two to tango, or it actually all depends on what happens to that one first star that evolves first. So I have the friendly version first, the happy one with the happy ending. I let you watch it. So this one star is evolving faster, and the other one offers help. It accretes a lot of new material until this guy loses all its envelope. This guy loses all its envelope, and the other one keeps some of it. So both of them look very happy. But do you think that the second star had a choice? If the material, the atmosphere of the star that it's evolving enters the gravitational potential of the second star, or even if the wind only, that you don't really need the whole star to enter, even if the wind enters, there will be mass transfer in between. So there will be dances there. And yeah, the second star doesn't have much to say. Yes?
But what does it mean that then it's free, the first one, like after it transfers the material, and then it can actually leave the couple?
Oh, in some cases it can get kicked out. Yeah, but it's a dead body anyway. No, yeah. So, for example, now I'm going to show you some examples of objects that we look at every day, and that are products of this tangle. They are products of binary interaction. These ones, for example, are close to the stars that I work with. So this is what I do every day. We have a star here that is like the sun, or it should be like the sun, but when we get the spectrum of it and we check which atoms it has, we check where those lines are, it doesn't fit. So it has chemical peculiarities, chemical elements on the surface that shouldn't be there, because the sun is too young to have made those elements itself. But there is a companion there, there is a wider, but we don't see it. So when we point our telescope to that star once, we see that it has chemical peculiarities, but we don't know what is coming from. Now, after many years, these stars were discovered, these chemically peculiar stars, because of binarity, were discovered in the 50s. So now when we see this, we know, okay, there is a companion there. Now we have solved the puzzle. And then we have to look at them for long enough to prove it, to see that those spectral lines are actually dancing. So this is an example. This is a happy ending dance in which both stars are still there, still in a binary system. These ones, planetary nebula, they are pretty, right? Not all of them are proven to be binaries, but there is a lot of people that thinks that, for example, so these stars are that short phase, it's actually the same one in the same position that I showed you before, that short phase when the red giant star is going to release all the material to the universe. If a star is spherical, it should release the material in a semi-spherical way, like the ring this one that I showed you before. That makes sense for a single star. But how do we explain things like this, for example? Or like this? How do we think that a single star dying just by itself can do these things? So there are a lot of people that think that all these funny shaped planetary nebula, this one is actually one, proven one, are a binary system. When the star was dying and releasing all this material to the universe, there was a second guy there orbiting around and shaping it. Some of them are proven, some others aren't. This is, I brought a toy. It's not mine, so don't lose it. Weird. So this is a star. That's something that exists, and it's there. And I have a 3D printed here to a scale, which scale?
1 to 200 billion.
Yeah, 1 to 200 billion. So this is the same guy, and he has been working on this single star for 3 years already. So these two stars are, do you want to play with the toy? You can pass it around, just don't lose it or he'll kill me. These two stars were born at the same time, maybe, we don't know. Michael, do you want to tell us more about it? They are just so close to each other that they are touching, like constantly touching. So this system orbits, and they are sharing material through this stellar bridge that was formed. And this is there, and it's stable in equilibrium. As much as you can be in equilibrium like this. But it's also a product of binary interaction that is there and that we are trying to explain. And one more, I think this is the last one that I have, is Eta Carina. I'm also not going to tell you how it formed because we also don't know. So this is a huge star, 150 to 200 solar mass when it was formed, and it's throwing a lot of material. I read today, because I wanted to tell you the truth, that it has thrown already about 30 solar masses to the universe, just this star by itself. And we know that for sure it has at least one companion, but it's too far to have an effect on this. So there are people who think that there was a third star involved at some point, and we don't know. But another very cool post-interaction product. So that's it, that's how I finished. I hope I have convinced you that the stars can be very different from each other, and that a lot of them are in binary systems. Yeah, they are as common as single stars like the Sun, 4 stars like the Sun, but much more common at higher masses. The stars, I forgot this one, I need to read my slides, if not I don't tell you. Not only there are a lot of stars, not only stars are very different to each other, but they will also change. So the Sun will be a red giant one day. And yeah, finally, the binary interaction products are very interesting, give us a lot of pretty pictures, and they are explosive sometimes as well. So that's it. Do you think it takes 2 to tango? That's it. Thank you.